Okay, so for this lab now, in our past one, we verified a bunch of laws that we've been studying in class here. But for this lab, another thing we like to do in physics is make predictions with our laws there. If all we ever did was verify science and we never actually did anything with it, it wouldn't really serve us much good anyway over here. So let's consider a setup for projectile motion, right? Here's the ground. Imagine we have some person or some projectile launcher that's going to launch a projectile from some initial height h off the ground at some angle with respect to the horizontal. So a very classic projectile motion type problem. Okay, so we know, of course, the path of this is going to look something like this over here. Okay, that dashed path over here, where, of course, we would call this horizontal distance the range. And, of course, the point up here is our maximum height. We want to go ahead and make a prediction about the motion of this. In other words, we want to figure out how is something going to actually land. We've done a bunch of practice problems calculating this stuff, but we haven't done any experiments with it. So let's, for this pre-lab, derive an expression, meaning like we'll start out with our basic kinematics equations, and then we'll apply some of the content knowledge we know here to come up with a new equation that represents the range of this particular object over here. One of the big predictions we like to make with projectile motion questions is how far is it going to actually go? All right, so thinking about the our equations of motion, we can write down one equation of motion for the x coordinate. It's going to be x equals to the initial position plus the initial velocity in the x direction times t plus 1/2 times the initial acceleration in the x direction times t squared, where t in this case represents, well, t is just general over here, but when t represents the total time of flight, x is going to be the range r in that case. Right, and so we know that the y equation, we can do something very similar. Y0 plus v0y times t plus 1/2 ay times t squared. And now we know a couple of things. So we know, for instance, that the acceleration in the x direction is 0. We have no acceleration there. And we know that the acceleration in the y direction, choosing up to be the positive, is going to be negative 9.81 meters per second squared. In this type of setup, we also generally know the initial velocity as well as the angle. And so we can come up with an expression to write down what is the initial velocity in the x. It's just the initial velocity times the cosine of angle theta. And what's the initial velocity in the y? That's just the initial velocity times the sine of theta, like we discussed in class. So, since ax is 0, this one's gone. And we essentially have those two terms over here. Now our end goal is to come up with one equation that's going to tell us how far this thing went, the range that this thing traveled over here. So, to do so, first thing we're going to do is take our equation for x right here, and we're going to go ahead and solve for t in this case. And then we're going to take that value of t and plug it into the y equation. Now, what we're doing right now, deriving this expression, is not something that would be expected of you on the AP exam or in this class. This isn't a big calculations-based class. But since I'm following along with you, I thought it would be fun if we did this slightly more involved calculation, so that way we can do a cool experiment with it. All right, so looking at my x position over here, I'm going to assume that my x0, I'll make a couple of simplifying assumptions as well, like my x0 is 0, that wherever I'm launching it from is my initial x position. Right, and I'm going to say that I can measure that quantity h. In this situation, this experimental setup, we know everything except the time and the range. We know the initial velocity and the angle. We know the initial height, the initial position, and we know the accelerations. We're just trying to find the range and the height over here. So given that x0 is 0 and h is y0, here I'll write that backwards, we can make a couple of substitutions to now begin actually solving this. Okay, so starting with that first equation with x, we have that x should equal v0x times t. Or in other words, that solving for t, we get t equals x, the x position of our object, divided by the initial velocity in the x direction over here. Now let's take this expression for t and plug it into our other equation over here. And we're going to see that it looks like we're going to get a big mess, but it's actually going to work out quite nicely for us into an okay formula. So taking that value and plugging it in using h for y0, we would get that y is equal to h plus v naught y times t, but t now I'm going to just plug in x divided by v naught x, because that's the expression we got for t from right above. Okay, and similarly I'll have minus 1/2 g, where g I mean just the value, 9.81, times t squared, which will be x over v0x, the whole thing squared. And this looks pretty ugly, but we can actually clean this up a bit. So first off, we know that v0x and v0y are just v0 cosine and v0 sine, respectively. So we can go ahead and make a few more simplifications. The h is just going to come along for the ride. And then v0y, we said, is just v0 times the sine of angle theta. And then v0x is just v0 times the cosine of angle theta. And then we just have a regular x over here. All right, and similarly over on that last term, minus 1/2 g times x over v0x, which is just v0 times cosine of theta, and then all of that squared here. And now if we notice this, the v0s in that second term will cancel out because there's one upstairs and downstairs. And then we also have sine over cosine, which is really just tangent of theta as an identity, but I'm going to leave it as sine over cosine for a second because we're going to do some simplification as well. So the next thing we can do now, returning to our picture, we're really interested in solving for the range. What's going on with the range is that the range is where the y value is equal to 0, right? Back when we've hit the floor, we've traveled our maximum distance. So now I'm going to go ahead and plug in 0 for y into this equation. And I'm going to replace x with r, because when y is 0, x is equal to r. That's just by definition what we're stating over there. So once we're on the ground, what this says is that our x position, what we have right here, is just equal to capital R, the range, which is the thing we're ultimately trying to solve for. And same idea over here, minus 1/2 g, and then I'll have r squared, because it would be x squared, and x is equal to r now, divided by v0 squared times cosine squared of theta. And I'm just going to rewrite this r squared for a second over here. Because when I do this, looking at this equation, it might not look like it. It might not feel similar to us. But this is actually a quadratic equation in R, meaning I'm pretending like the R is like x. In a general quadratic equation, ax squared plus bx plus c equal to 0. Right? If you pretend that R is like x, then the coefficients of R are the a, b, and c for the quadratic formula, which we can go ahead and plug into. So our quadratic formula tells us that the solution to a quadratic equation, x, or in this case, R, is equal to negative b, that's negative coefficient of the linear term, that's this one. So it's going to be negative sine over cosine, plus or minus square root of b squared, so that's going to be sine squared theta over cosine squared of theta, minus 4 times a, well, a is the coefficient of the squared term, so that's all of this stuff here, this big mess, negative 1/2 g times v0 squared times 1 over v0 squared cosine squared there. So I'm just going to write it and keep it nice and neat for me. So for a is going to be g over 2 times v naught squared cosine squared theta. And then times c, which c here is always the constant term, the one without the x, or in this case the r, so that's just h. Now, if you're having a little panic that you wouldn't be able to do all of this on your own, well, don't worry, you wouldn't have to. Not right now. And you go take physics in college, you might have to do a derivation like this. But just follow along with me for now. Okay, so now that we have this over here, all over 2 times a, so that would be 2 times, once again, a was negative g over 2v0 squared cosine squared of theta. And this right here is a good equation now for the range. We've solved for the range. We could go ahead and plug in values to this, like where theta is our angle of launch, and h is our initial height of launch, and v0 is our initial velocity. We could plug in and get an answer here, except this looks super ugly. So let's clean it up a little bit and just try to simplify it. So I'm going to start out looking at the denominator. Right, first off, those 2's will cancel. That's easy enough. And then my denominator is negative g over v0 squared times cosine squared of theta. So I'm dividing by a fraction. Remember, when you're dividing by a fraction, you're really multiplying by the reciprocal. Maybe in algebra class, you might have called this like keep, change, flip or something, where you keep the numerator all by itself. You change it from a division sign to a multiplication sign, and you flip the denominator. So doing all of that, then I would get that r equals... flipping up the denominator here, negative v0 squared times cosine squared of theta divided by g. That's just from flipping the term in the denominator. And then I have all that other junk still, negative sine of theta over cosine of theta plus or minus square root of sine squared theta over cosine squared theta minus, I'll clean this up a little bit too, those coefficients cancel out, I'll get minus 2 times g times h divided by v0 squared times cosine squared of theta. Which still looks kind of ugly, but it's a little bit cleaner, and we're on our way to making it even better now. So I just added a page, and now let's move on with this. So another thing to take note of here is that there's a factor of cosine squared in the denominator of every term under this radical here. So let's factor that out of those. So now I'm going to keep the front just the same, negative v0 squared times cosine squared of theta divided by g, negative sine of theta over cosine of theta, plus or minus, I'm going to take a 1 over cosine squared theta out of every term there in the radical. Sine squared theta minus 2gh over v0 squared. And all of this is under the radical. Well, that's really good for us now, because if I have a 1 over cosine squared under my radical, that means I can do 1 over cosine outside the radical. In other words, I could take the square root of that little term here. And simplifying a little more, step by step. All right, we have our first term still, then I get negative sine of theta over cosine of theta. And then, like I said, the square root of 1 over cosine squared is just 1 over cosine of theta. So we can take that out of the radical. And we're left with all of this stuff in the radical still. And then the last couple things we can do to clean this up a little bit, you notice that we have a cosine squared upstairs here, and then every term has a cosine in the denominator of the equation over here. So we can cancel out these cosines with one of these factors of cosine up here. So that guy's gone, and these are gone. And then the last thing we can do is distribute this negative sign to everything. When I distribute this negative sign to here, that's obviously going to turn positive. But if I distribute a negative sign to this, remember the plus or minus really means there's 2 roots of this. So if I flip this to, if I multiply a negative by this, I'll get minus plus, but that's the same thing. It really doesn't matter. It's still just telling us, again, there's 2 roots. So I'll just distribute that negative sign, and then I'll get our final version of the range equation in its full glory. V0 squared times the cosine of angle theta divided by g. And then all of that times positive sine of theta, because we distributed that negative sign, times plus or minus, because like we said, there's 2 solutions there anyway. They'll both just flip signs. Plus or minus square root of sine squared of theta minus 2gh all over v0 squared. And that took me about 10 minutes to derive because I was going really slowly, narrating every little step. But really all we did was start out with our basic kinematics equations over here. Then we listed out everything we knew over here and made a couple of substitutions, plugging it into our equations. And then just some rewriting and solving a system of equation. It looks messy, but to be honest, once we got our assumptions down over here, And once we knew what our kinematics equations were, from here on is pretty much just algebra. It's just there was a lot of it. You won't have to do that much algebra in class or on a test. But since I was narrating through, I thought we were strong enough to handle it over here. And this equation, now that we've actually solved it doing that algebra, will predict the range of some projectile shot at an angle of theta with an initial velocity of v0 that is near Earth, that has g over here. Okay, and this little h, remember, is that initial height that the projectile is launched from. So if we can measure h, if we can know v0, if we know theta, we can now figure out how far something is going to go. And if you look at it, we never actually had to solve for the time. We had to solve for it originally to eliminate it, but independent of time now, this is when we hit the floor. Again, right? That's essentially what we did with time by plugging that in over here. We eliminated it. And then we were able to, we eliminated time from the y equation. And then by setting y equal to 0, we noticed that that means the equation is on the floor. So that means that we're at the range. And long story short, you don't need to know how we did that derivation. I'm not going to ask you to do that again. But we can now use this formula to make predictions about the motion of a projectile, which is exactly what we're going to do in today's lab.